RLC circuits is going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now in this lesson, we're going to talk about specifically RLC series circuits, which have a resistor, an inductor, and a capacitor in an AC or alternating current circuit. Now we'll talk about the difference between the max voltage and the RMS or root mean square voltage, as well as the max current and the RMS current. We'll talk about the capacitive reactance and inductive reactance associated with both capacitors and inductors, and how they combine with the resistance of the resistor to form the overall impedance of the circuit. We'll also talk about the phase angle in such circuits, as well as the resonant frequency. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. Now in the last chapter, we learned about generators and how they set up an alternating current where the polarity of the potential as well as the current changes directions in a sinusoidal fashion. And so it turns out it follows this lovely equation right here where delta V is equal to delta V max times this sinusoidal portion that's related to the frequency of the generator. We can see here that this kind of follows that sinusoidal pattern, and there's our max voltage on the positive side and then on the negative side. So in this case, positive and negative are really arbitrary. It's just both directions. So we're going to set up a potential difference that will cause the current to want to flow one direction, and then it will reverse polarity and go back and flow the other direction. So we take a look at that corresponding current, and we can kind of think of if this only involves a resistor, the current would look potentially something like this. So in here we'd have Imax as well. And so the current flows in the same direction as the polarity as the voltage, according to Ohm's law. And in this case, the potential difference and the current are directly proportional. And because they're directly proportional, it turns out they're also in phase. So if you notice, they hit zero at the same points, they hit maximums, so as well as minimums or maximums with the opposite polarity at the same points as well. And they are in phase when all you've got is a resistor in the circuit, it turns out. Now, one thing we have to talk about, and that's the power being dissipated by such a circuit. And we have an issue here because if we look at the average voltage or potential difference here, well, it's zero because half the time it's positive and half the time it's negative, and the average comes out to zero. And if we take a look and say, well, what's the average current in this lovely circuit? And we say, well, the average here, is positive for the first half, negative for the second half, and the average current in the circuit's also going to be zero, all with this reversing of polarity. Well, those aren't super helpful. If we take a look at the power in such a circuit, you might recall that we said power is equal to delta V I, or one other way we expressed this was I squared R, and we have a problem here. So if we want to know what the average power in such an alternating current circuit is, we might be inclined to be like, well, the average current is zero, so the average power has got to be zero. But it's not. So it turns out a resistor doesn't care which way the current is is flowing through it. It's going to dissipate power in both directions. And so we can't just plug in some sort of average current here that is zero and come up with an appropriate amount of power being dissipated in the circuit. And so what we use is what's called the root mean square current and voltage in such alternating current circuits. That gives us a better idea of what's really going on. That doesn't, kind of factors in this change in polarity, doesn't change what's happening inside the resistor, so to speak. All right, if you take a look, what we do is ultimately we square all the values for both voltage and current. If you square them all, it makes them all positive. And so if you square delta V here, it would look like so, but larger, and then also here, and then we go back and sum those all together and go back and take a square root. And that square root is going to end up giving us something kind of an intermediate value. And it turns out, you go back and do this process, you get a value for this delta V RMS equaling delta V max divided by the square root of 2. And we've got an analogous equation for the current as well, where, not delta, where the RMS current, again standing for root mean square, is equal to the maximum current divided by the square root of 2. And ultimately this means about, just north of 70%, this root mean square is roughly 70% or 71% of the maximums in either of these quantities. And it is that root mean square that kind of gives us an overall kind of a new kind of average that helps us actually calculate this average power. And so this average power being dissipated here ends up equaling the root mean square current squared times the resistor, and that will actually give us an adequate value. It is just as if we had a DC circuit with this lovely current, and it would be the same power being dissipated. So that's kind of the utility of using this root mean square, both current and voltage. And we'll use this kind of routinely throughout this lesson. Now we set up Ohm's law here just a little bit ago. So, and Ohm's law is going to take on a little bit different flavor here because we've got different points in time, but it's true at every single point in time. And so a couple key points in time we take a look at might be the maximums. So delta V max equals I max times R, or with the RMS it works as well. So delta V RMS equals I RMS times R as well. And so again, it's true at any point in time, including the maximums, but it's also true of the overall root mean square as well, and we can set up Ohm's law in accordance. But again, key thing to keep in mind here is whether you're using the maximum or any other point in time or the RMS is that delta V and I are directly proportional and are exactly in phase on this lovely plot of the potential difference or voltage versus time. So now we want to take a look at capacitors in AC circuits, and if all we had was a capacitor in an AC circuit, the voltage would still be sinusoidal, but it turns out the current would no longer be in phase with the voltage, and we'll kind of see why. Now, a little reminder from RC circuits where we saw the charging of a capacitor. And so as you charge up a capacitor, its Q goes from 0, the charge goes from 0 up to a maximum value of C times delta V. So, and Q reaches a maximum when delta V reaches a maximum. So, but your current goes the other way around. So you get the maximum current flowing when there's no buildup of charge on the plates. But as more and more charge builds up on the plates, it's harder to add more positive charges to the positive plate or more negative charges to the negative plate, if you will. So, and therefore the flow of current goes down until it asymptotically approaches 0. And so the big thing to get away from this is that over time, delta V approaches a maximum when Q approaches a maximum, but that's when I, the current, approaches a minimum. There's an inverse relationship between the current and delta V. So going back up here, if we want to kind of plot current on the same graph here, we can see again when delta V is 0, again Q is 0 because delta V must be 0 as well. They're proportional to each other. So if Q is 0, so is delta V. And when delta V is 0, that's when current is at a maximum. And so here we've got delta V 0 here, here, and here, and that's when current's going to be at a maximum. And the other way around, we can also say that when delta V reaches a maximum, that's when the current's going to drop down to 0. And so we can plot some points here. So where do we have delta V being a maximum? Well, right here, and that's where the current here is going to be 0. Okay. And again, going the other way, when delta V is at a maximum, current is 0, and then when delta V is 0, the current's going to be at a maximum. So delta V is 0, the current's going to be at a maximum, we'll change polarity, and it'll be at a maximum in the opposite direction, and we'll change polarity again, maximum in the other direction. And we can kind of see what this graph looks like now of our current with our max current right there at the beginning. And if we see here, so again, your current and your voltage are not in phase at all. And so if you look at the voltage is like, okay, I'm starting at 0, I'm gonna reach my maximum here. And he kind of looks back and like, oh, the current already reached its maximum. And then he drops down and he goes down to 0 and he's like, oh, the current had already reached 0 a little while ago. And then he drops down to his maximum in the opposite polarity. He's like, oh, the current was already at its maximum in the opposite direction a little while ago. And so what we say here is that the voltage lags the current, and we say by 90 degrees, by a quarter of a wavelength, if you will, a quarter of 360 degrees. All right, so that is capacitors, and we can make an Ohms-like kind of equation for capacitors as well. So instead of delta V equals IR, we have the capacitive reactance XC here instead. And so it turns out XC is equal to 1 over 2 pi times the frequency times the capacitance, and it has units of ohms by the time you plug in the frequency in hertz and the capacitance in farads. So this capacitive reactance comes out with units of ohms, as it should if it's being kind of taken the place of resistance in Ohm's law. Now, one thing to note here, sometimes we'll write this give myself a little room here, delta VC across the capacitor, root mean square, is equal to the root mean square current times that capacitive reactance yet again. So, and the only thing I want to do from here is just make this make sense, that there's this inverse relationship between the capacitance and the capacitive reactance. So if you look back over here, not only is the charge built up on the plates of a capacitor proportional to delta V, it's also proportional to C, the capacitance. So higher capacitance, higher charge is going to be built up on those plates. Well, if you're going to build up more charge on those plates of the capacitor, you're going to need more current to flow, which is supplying the charge to be built up on those plates. And so higher capacitance, higher current. Well, if you got more current, you must have less resistance, or in this case, less capacitive reactance. It's kind of the effective resistance for a capacitor. And so in this case, we can see that inverse relationships. So again, higher capacitance, higher current, lower capacitive reactance. So higher capacitance, lower capacitive reactance, this inverse relationship makes sense. Let's store those for later. So now we're going to take a look at inductors in AC circuits. And if all we had was an inductor in an AC circuit, so again, we're still going to have the sinusoidal plot of voltage versus time. So, but once again, we're going to find out that the voltage and the current are not going to be in phase, but in the opposite direction as to what we saw across capacitors. Now keep in mind what we learned in the last chapter, that the back EMF across an inductor, or associated with an inductor, is proportional to the inductance of the inductor, but is also proportional to the change in current. In fact, that's how we define kind of what inductors do, is they oppose the change in the current, or the rate of change in the current. So keep that in mind. We're going to use that to kind of plot the current superimposed onto this graph. Now, if we go back and look at current here, my question for you is this. So in looking at the graph of current versus time, when is the change in current 0? And when is the change in current at a maximum? And so this is going to be a little bit tricky. So we get this down. So the change in current is 0 when the slope of this graph of current versus time is 0. And when is that slope 0? At the maximum and the minimum. That's when the slope goes horizontal, if you will. The slope is 0. And so when the current's at a maximum, the change in current is 0. Now what about the other way around? When is the change in current at a maximum? Well, it turns out the change in current's at a maximum. The maximum slope, when the current itself is 0, that's when the change in current has the steepest slope in either direction. So keep that in mind when we go back to plot it over here. And so delta V is going to be 0 when delta I is 0. The change in current is 0. And the change in current is 0 when current is at a maximum. And so delta V is 0 here, here, and here. And we're going to, it turns out, go from the one direction in the polarity, and when delta V is 0, to the other direction in polarity, and then back to this direction in polarity here. So, and then the other way around is, when is delta V going to be at a maximum? Well, when delta I is at a maximum. And when is delta I, the change in current, at a maximum? When the current crosses through 0. And so delta V is at a maximum because the current is crossing through 0. Delta V is at a maximum in the opposite direction because the current is crossing through 0. And we can kind of see what our graph is going to look like here now for our current flowing through time. And if we look here now, no longer is the voltage looking at the current and saying, oh, the current's already been here. So the voltage is going to reach its maximum, and he's like, oh, current hasn't got here yet. I'm leading that current. So voltage is going to drop back down to 0, and it's like, oh, the current hasn't got there yet. I'm leading the current. And so that's what we say here, is in this case, we say that the voltage leads the current. And it's again by 1/4 wavelength, or by 90 degrees here. So with capacitors, the voltage is going to lag the current, but with inductors, the voltage is going to lead the current in either case by 90 degrees. All right, once again, we can make an Ohm's law-like equation out of this, where delta V equals IR. Well, in this case, delta V equals I times now the inductive reactance, X sub L, instead of X sub C. And this inductive reactance is equal to 2 pi F times the inductance. And if you plug in the frequency in hertz and the inductance in henries, so then your inductive reactance here will have units of ohms, just like it should if it's taking the place of resistance here in an Ohm's law-like equation. Now we typically write this as delta V L RMS with I RMS as well, similar to what we did with capacitors. So the last thing is we want to make sense of why here the inductive reactance is proportional to the inductance, kind of the opposite relationship we saw between the capacitive reactance and the capacitance. Well, we can kind of make sense of this. So if you recall this back EMF is proportional to the inductance. And this back EMF is opposing the current, if you will. And it's really opposing the change current, but it's an impedance to the current, if you will. And we'll use that word a little more specifically in a little bit. So, but it's resisting the change in current and kind of the current as well with this back EMF. And so the greater the inductance, the greater the effective resistance the inductor should pose. And that's exactly what we see here with the inductive reactance being proportional to that inductance. So now we're going to finally deal with an actual RLC series circuit, which is supposed to be the main topic of the lesson, but we had a lot of preparation, and everything up till now is that preparation. But we've got a resistor, an inductor, and a capacitor, along with an AC generator in series in a circuit. And the problem we're going to run into is finding the overall delta V. Now, it turns out, so we got a lovely simple sinusoidal relationship between I and I max. So, and the current in any one of these components is going to be the same all the time. Now, it is going to vary sinusoidally, but it will be the same in every component at any given point in time. So the voltage across each is going to be different though. So if you recall, we said that the voltage across the resistor is in phase with the current. We can see that kind of on this graph in blue for the voltage across the resistor and red for the current. So, but the voltage across the capacitor is going to lag the current by 90 degrees, and we can see that. And then the voltage across the inductor here in green is going to lead the current by 90 degrees. And so if we want to find the overall delta V max of this circuit, so because they're out of phase, we can't just say, well, just add the delta V max of the resistor, the delta V max of the inductor, and the delta V max of the capacitor all together and get the overall delta V max of the circuit. Well, that's not going to work because they don't all hit delta V max at the same time. If they did, then you could just add them together. We'd say they're in phase, but because they're out of phase, we got to come up with a way to kind of take that into account. And we do that using what are called phasor diagrams. So in the phasor diagram, what we're ultimately going to do is we're going to plot kind of on the positive x-axis, which I'll identify as 0 degrees. That's where we're going to plot the current. Maybe I'll stay consistent here and plot that in red. And I'm not actually going to put it on the graph here. So, but the current would line up with that positive x-axis. So, and from that, then we can see that the voltage across, and let's do the resistor first, would be in phase with that. So, and therefore also line up with that positive x-axis. So the voltage across the capacitor would lag that by 90 degrees. So it's going to be 90 degrees behind that. And then finally for the inductor, it's going to lead the current by 90 degrees and therefore be in the positive y direction on this plot. So, and there we go. And what we're going to ultimately do is we're going to add these three together as vectors. So to account for the fact that they're out of phase, add them as vectors to get the overall delta V max. And so if we look here, so we can actually kind of simplify this down into kind of adding two vectors together, if you will. And so one of those vectors would simply be delta VR. So, but the other vector, so is going to be a combination of delta VL minus delta VC. And overall, if delta VL is larger, then it's going to point up if delta VL is bigger than delta VC. So, but if delta VC is bigger than delta VL, then this other component of the vector would actually point down. So, and then we'd find the vector sum of those. All right, so let's label these a little better. So this would be, let's keep our color coding arrangement going. So this is going to be delta VL minus delta VC. And then our overall vector sum is going to be delta V max. And the angle here, phi, is going to be the phase angle between the maximum voltage and the current, which again we said, so we've defined as being on that x-axis. So that's kind of overall what we're doing here. Now notice that what if, delta VL and delta VC were equal to each other? Well, then they'd cancel effectively. So, and the overall voltage across the resistor would be all that was left, and it would be equal to delta V max. And will be a special case we'll deal with in just a little bit. Now, keep in mind a couple of things here. So, one, recall that delta VR is equal to IR. So, delta VL is equal to IXL, and then delta VC is equal to I times XC. So we've got these three lovely relationships here. So if we go to find delta V max right here, so if we add them as vectors here, so delta V max, well, to add these as vectors, we'd have a squared plus b squared equals c squared, and we take the square root to get back to c, and so it'd equal the square root of delta V r squared plus delta VL minus delta VC all quantity squared. Cool, so a squared plus b squared is right there, and then we take the square root to get delta V max. So that's ultimately what we're doing here, but then we're going to substitute in, so for delta V of the resistor, IR, delta V of the inductor, IXL, and then delta V across the capacitor is IXC, and plug them back in and make a new phasor diagram here instead. And so what we're going to find, though, is that we can make an analogous phasor diagram here. Oh, I'm going to run out of room here. So where this is equal to R, this is equal to XL minus XC, and the overall vector sum is going to be a new quantity that we're going to call Z and call the impedance. And in using this impedance, ultimately what we can say is that delta V is equal to, let's actually center this on the diagram, so delta V is equal to IZ, where Z is that impedance. It's going to have units of ohms, and in this case, if I want this to be the max value, you can use it at the max value. If you want it to be RMS, you can do that as well. So since delta V RMS and delta IRMS only vary from delta V max and delta Imax by dividing by the square root of 2, a common factor. So it works in both cases. And so now we've got a simple expression looking like Ohm's law for the RLC series circuit as well. And so, and again, if you can kind of keep this looking like adding up vectors to get this overall impedance using the resistance of the resistor, and again, this difference of XL minus XC, so for the inductor and the capacitor, great, you have one less equation to memorize. But if you just want to memorize this equation, which then ultimately turns into this equation for the impedance, so R squared plus XL minus XC squared. Ultimately the same thing to get the impedance, and then you can use the impedance in such a relationship to figure out delta V max and its relationship to Imax. Oh, let's do one other thing here. So this phase angle, phi here. So notice we can get that phase angle in one of a couple different ways. So with vectors, we used to say that tangent theta is equal to the y component over the x component. Well, in this case, you could say that a couple of different ways. You could say that tangent of phi is equal to the y component over the x component. So in this case, it could equal delta VL minus delta VC over delta VR. Or you could look at it from this perspective as well and say that tangent of phi is equal to XL minus XC all over R as well. So y component over x component. And so then you could take the inverse tangent of that ratio to figure out what that phase angle is. Okay, and we'll come back to some importance for that phase angle in just a little bit, but I think we're ready to do a little bit of plugging and chugging. All right, so we've kind of summarized our entire list of equations up till this point, and got a couple different questions. We'll start with an easy one, and then we'll start with the one that applies specifically to this RLC circuit off to the right here. So, but the first question says, the peak voltage for a home in the US is 170 volts. What is the RMS voltage? And then the second part of the question says, what would be the RMS current through a toaster having a resistance of 12 ohms? What is the power dissipated by the toaster for part 3? All right, so we got the peak voltage, the max voltage, and we want to get the RMS voltage, and all we got to simply do is divide by the square root of 2 there. And so in this case, delta V RMS is going to equal that peak voltage of 170 volts all over the square root of 2. We'll let our calculator do the heavy lifting for us here. So good chance if you're at all familiar with some electrical work, you already know the answer to this one. So about 170 divided by the square root of 2 is 120.208. And if we round to 2 sig figs, it's going to be 120 volts. All right, second part of the question says, what would be the RMS current through a toaster having a resistance of 12 ohms? We can simply use an Ohm's law relationship here. So where delta V RMS equals I RMS times that resistance. So if we rearrange this and solve for that I RMS, it's going to equal the delta V over the R, which in this case is going to equal that 120 volts we just calculated, divided by that 12 ohm resistor. So I'm making the math easy here, and it's going to be 10 amps. Now we got a problem. I want 2 sig figs, and I got a couple different ways of getting that. So I can put a bar over that and say 10 amps, or I can say 1.0 times 10 to the first amps. Either way, I got 2 sig figs for that RMS current. And then finally, the last part, what is the power dissipated by the toaster? And again, if it's just a simple resistor in an AC circuit, we've got a lovely formula for that here. And so average power is going to equal the RMS current squared times the resistance, which in this case we just figured out was 10 amps. We'll square that times the 12 ohms. 10 squared is 100, and times 12 is 1200. And that is in units of watts. All right, so not so bad so far. And now we'll go and deal with the RLC circuit proper. Now this is going to be a 4-part question. And we're only prepared to do the first 2 parts. Then we got to go back and learn a couple things to do the remaining 2 parts. But the first 2 parts, so dealing with this lovely diagram, we've got one little piece to add, my bad. So the frequency of the AC generator is 60.0 hertz, which turns out is what it is in typical US household, so at the house. So, all right, first part of the question says, what is the impedance in the AC circuit in the following diagram? Second part says, what is the RMS current if the RMS voltage is 120 volts? And then parts 3 and 4 we'll have to come back to in a little bit here. So first part 1 is the impedance. So in the impedance Z here, so we figured out quickly how to calculate, but we're going to need the inductive reactance and the capacitive reactance first as well. And so in this case, your inductive reactance was equal to 2 pi FL, which in this case is 2 pi times 60 hertz times, and in this case, our 2.0 millihenry is going to be 0.0020 Henry. And once again, we'll let our calculator do the heavy lifting for us. So 2 times pi times 60 times 0.002. In this case, we're going to get 0.754. And my final answer is going to have 2 sig figs, but I'm going to carry 3 all the way through till the end. So 0.75398, so 0.754 ohms. All right, we also got to calculate the capacitive reactance here, which is 1 over 2 pi FC, which in this case 1 over 2 pi times 60 hertz. So, and I made the numbers nice. They're all kind of similar here. So 2.0 millifarads here is again going to be 0.0020 farads. And once again, we'll let our calculator do the heavy lifting for us. I'm actually going to use my last entry and just do 1 over that last entry, since I made the capacitor the same numerical value anyways to the inductor. All right, so to insert that in, 1 divided by parentheses, and then we got an added parentheses at the end. And so 1 divided by 2 pi 60.002 is going to get us 1.32629, and again, rounding to 3 sig figs, 1.33 ohms. All right, now we can calculate Z. And again, Z is going to equal the square root of R squared plus XL minus XC squared, which in this case is 2.0 ohms squared plus 0.754 minus, and in this case, 1.33. Those are in units of ohms, and then we'll square it. All right. Once again, we'll let our calculator do the heavy lifting. So we're going to have 2 squared. You know, let's do it all in one shot. So square root of parentheses 2 squared plus another set of parentheses, 0.754 minus 1.33. And now we'll close one set of parentheses. We'll square that. And then we'll close another set of parentheses for the square root. We're going to get 2.08129, and 3 sig figs will round out to 2.08 ohms. And technically, actually, I should be rounding this to to start at 2 sig figs. So technically, the right answer is 2.1 ohms. When I go to use this in the next part of the calculation, I'll use that 2.08. I like to carry 1 extra sig fig until I get some final answer that's being asked. And the second part of this question says, what is the RMS current if the RMS voltage is 120 volts? And once again, we can use Ohm's law now, or at least this version of Ohm's law for an RLC series circuit. So we'll solve for that IRMS current. It's going to equal delta V RMS over Z. Told that delta V RMS was 120 volts, and now we can plug in that 2.08 ohms for the impedance. And so 120, and I'm just going to divide by the last answer in my calculator, and 57.656, and I'm going to round that to 2 sig figs and round it up to 58 amps. Okay, so that is the first 2 parts of this 4-part question. So the third part is going to ask us what is the resonant frequency, and the fourth part is what is the average power dissipated, neither of which we have talked about just yet. So we're going to have to get just a little bit more out of this. Let's make some room. So the third part of this question was what is the resonant frequency of the circuit? So we had a frequency of 60.0 hertz. It was not the resonant frequency. And so the resonant frequency ultimately is when XL and XC have exactly the same magnitude so that they cancel. There ends up being no Y component to the impedance. And in such a case, then the impedance would just simply be along the x-axis and be exactly equal to R. And that's when your overall impedance would be at a minimum, when it's simply equal to R and there's no additional contribution, so to the inductor and capacitor. Well, it turns out this happens at a specific frequency. So, and the key is realizing that your inductive reactance and your capacitive reactance have to be equal. So, and that's kind of how we can solve for that condition of resonance here in this case. And so here we'd have 2 pi FL equaling 1 over 2 pi FC. If we rearrange this to solve for F, so in this case I'm going to multiply both sides by F, and we're going to get F squared on this side. So I'm going to divide through on this side, and we're going to have 1 over 2 pi C times 2 pi L. So, and then we'll take the square root of both sides. And notice we've got a 2 pi times a 2 pi, and when you take the square root, you're just left with one of the 2 pi's. And so in this case, F is going to equal 1 over 2 pi times the square root, and we still have a square root of C and a square root of L, and so square root of L times C, and we give this a little F naught, and this is the condition for resonance in an RLC series circuit. And you can just plug in the value of the inductor, so the value of the capacitance, and calculate out this resonant frequency, which is exactly what we're going to do here. So, and both of these were 0.002. So notice we're going to 0.002. So, and in this case for the inductor, that's going to be in henries. So, and for the capacitor, it's going to be 0.002 farads. So, but when you take the square root of 0.002 times 0.002, you're just going to get 0.002, right? So this reduces down to 1 over 2 pi times 0.002. So in being a frequency, this does come out in hertz, provided we've used SI units. So for both the inductance and the capacitance, which we have. So 1 divided by parentheses 2 times pi times 0.002, close parentheses, and we're going to get 79.577 hertz, and rounding up to 2 sig figs, it's going to round up to 80 hertz, which, again, to get 2 sig figs, I either put a bar over the 0 or I make this 8.0 times 10 to the 1 hertz. All right, so that's the third part of the question, and we've got the fourth part of the question. So in the fourth part of the question is, what is the average power dissipated? Let's make some room for that. So now we want to find the power dissipated in our series RLC circuit. So, and to do this, we have a little bit of a problem. Now, we should realize that power is only being dissipated across the resistor. So as current flows through the inductor, So it establishes a magnetic field in a certain direction. Well, then you reverse the polarity and current flows the other way and undoes that magnetic field, then forward and flows in the opposite direction. As you do this over time, there's no net power being dissipated. So same thing with the capacitor. So when the current flows in one direction, you're going to have a charge buildup, so aligning with that polarity, but then you're going to reverse the polarity of the current, so and undo that charge buildup and then build it up in the opposite fashion. And you're going to do this over and over and over again, and there's no net power being dissipated at the capacitor either. So, but again, your resistor doesn't care which way the current's flowing through it. It is going to dissipate power, usually in the form of heat. So whether current's flowing one way or the other, and that's where the power is going to be being dissipated in our RLC series circuit. So it turns out what we want to do here for that average power, so is take the delta V RMS times the R RMS. Now, one thing to note, we said back a little bit ago that this was a formula for the average power being dissipated, so for a resistor in an AC circuit, but when there's only the resistor there. So, and we also saw back with DC circuits, we saw that power could be expressed three different ways. I squared R, so delta V times I, or delta V squared over R. So, well, this is the one I want to use, and there's a reason I want to use this version of it right here. So, because it turns out it's going to be a little bit incomplete. So if we take a look back at our phasor diagram, so, and recall that the current lined up with the x-axis. So, and unless we're at resonance, assuming we're not at a condition of resonance, well then you're going to have some vector sum here for delta V RMS, and it's going to be out of phase with the current by a factor of phi. And so again, if you're under resonance and XL equals XC, well then by all means, then phi is going to equal 0, and they'd be in phase, and you could simply just use this formula and life would be good. So, but if they're not in phase, and typically the case, typically not under resonance, you got to factor that in by multiplying by cosine of phi. So, and now we're ready to actually calculate out this average power. All right, well, we know the delta V RMS in this case is 120 volts. So, oh yeah, we did that somewhere. I just erased it. That's why we lost it. So 58 amps. And then we got cosine of phi. But we never actually calculated phi, that phase angle. So recall that we can calculate that phase angle using the inverse tangent. In this case of XL minus XC, the Y component of the impedance, all over the X component of the impedance, the resistance, and go from there. So XL was the 0.754 ohms. I transferred that over because I knew we'd need it. So minus the 1.33 ohms, all over our resistance of 2.0 ohms. Let's see what that angle comes out to. All right, inverse tangent, parentheses, and I'm going to put two sets of parentheses here. So parentheses, 0.754 minus 1.33. I'll close one of the parentheses, divided by 2.0, close the other one. Is the inverse tangent of all that. It's going to come out to negative 16 degrees. So in our case, that just means it's actually down here instead because XC was actually bigger than XL. All right, so we'll plug that in here, negative 16 degrees. So I might recall that cosine, whether it's 16 or negative 16, is going to give us the same value, at least same magnitude overall. And so 120 times 58 times the cosine of negative 16. Doesn't like my syntax. Let's try that one more time. Oh, I didn't put an extra parentheses in there. So cosine of negative 16, it's going to get us 6690, which I could round up to 6700 for 2 sig figs. We've kind of gone through all the lovely calculations you might see for an RLC series circuit. So again, you might have to calculate the impedance as well as the phase angle associated with it. You might have to calculate the resonant frequency, and you might have to deal with the average power being dissipated on top of just simple calculations for the delta V RMS, IRMS, things of that sort. If you have found this lesson helpful, please consider giving it a like. Happy studying.